In this video, Dr. Jordan Peterson explains how different motivational systems work together and against each other.
Oh, because their male sexual behavior is harder to organize. And so decorticate males can't mate. So if you ever meet a male who can't mate, then, anyways. Sorry. But that's the reason, is that there's certain elements of male sexual behavior that require more complex organization. So that's one thing a decorticate male can't do. So it's easier to distinguish them from females, from the female cats. That's the only reason. So okay, so you get the idea. So like at the bottom of the brain there's all these systems that are really alive and sort of on fire, and they're all generating up these motivational frames of reference, and they do that. That's instinct, so to speak, and then all of that's elaborated up by the cortex, and the cortex is saying, okay, well, these things are like a pack of fighting 2-year-olds. So by the way, and I mean that because if you take children and you put them in age-matched groups, and so you have a group of 18-month-olds and 2-year-olds and 3-year-olds and 4-year-olds and so on, all the way up to 16-year-olds, say, and then you count violent interactions, kicking, hitting, biting, stealing. The 2-year-olds are like, they're just all over that, But it's not actually quite right, because some of the 2-year-olds are peaceful and passive, but there's a subset of the 2-year-olds that are like chaotic motivational machines, right? They're just running around being as impulsive as can possibly be, and you can think about them as almost under complete hypothalamic control. They're just cycling from one intense motivational state to another. That makes 2-year-olds a blast. Like, they're really fun to be around, except they're kind of a pain in the neck. But they're really fun because they're really on fire. They're into this and into that and into this, and then they fall down because they're too tired, and then they wake up and they're starving to death, and they're really alive. But then what has to happen is that those behaviors, those motivational states, which are sort of working in isolation, they start to conflict with one another, so that the child can't really organize any medium to long-term behavioral strategies, being that impulsive. So what the cortex is there for is to start sequencing those motivational systems in higher order structures that allow each of them to get what they need in order to function across long periods of time in increasingly complex social environments. That's what the cortex is for. So it's a complex regulatory mechanism. And what it's doing is it's like a nuclear reactor. The core is really hot and fiery. And you need to sink rods into it to keep it under control, to dampen it. And that's really, it's a good analogy for how your brain works, because the underlying systems, they're on fire, they're alive. And the cortex is saying, well, a little bit of you now, and a little bit of you, and then some of you, and wait your turn, and so on. And it sequences out over long stretches of time. That's really socialization. And that's quite a different view than the Freudian view of repression. Because I would say you only have to repress a motivational system if you're not very successful. Because if you're a successful and well-socialized person, you don't have to suppress them or repress them, you just have to sequence them. That's all, because they're all going to get what they want, right? And that means that you're a good player of complex social games. And that has very little to do with repression or inhibition. It's just sequencing. It's important. It's important. What time do we have? Oh, so here's kind of an interesting way of looking at the amygdala. This is from Joseph Ledoux, who wrote a lovely book on the amygdala. And it also kind of shows you how your body is structured. And so, I don't know if you've ever heard of the phenomena of blind sight. Do you know what blind sight is? Did I tell you about blind sight, or did you learn it somewhere else? Okay, well anyways. One way of being blind is to go like this, and then you can't see. And another way is to have your retina destroyed, and maybe the optic nerve could go. And another way of being blind is to have your visual cortex destroyed. The thing that's weird about having your visual cortex destroyed is that you think you can't see, but you still can. You just can't see the same way you saw before, and you can't see objects consciously. But if someone says, I've got one hand up, which one is it? And they say, well, I can't see it, and you say, guess, then they can guess. And so you might say, well, how can that be? And the answer to that is that, okay, imagine for a minute that the world isn't made out of objects. Imagine that it's made out of patterns, because it is made out of patterns. That's why music is so intensely interesting, because it's a representation of the world as a place of patterns. And a pattern is something that repeats, because otherwise it wouldn't be a pattern. And the only thing you really need to keep track of things that repeat, because there's no point knowing anything about things that don't repeat. Because what the hell good is your knowledge? So the world's full of patterns. What happens is that that pattern is transformed into a pattern on your retina. It's a pattern of neural activation. And then there's multiple branches from your retina. It doesn't just go one place, it goes lots of places. And each of those places it goes produces its own implementation of that pattern. And one of those implementations allows you to see the world consciously. But other implementations have other functions. So for example, if you show someone with blind sight an angry face, and you record their psychophysiological responses, and you show them a neutral or smiling face, you can distinguish their physiological responses to the angry or fearful face from the happy or neutral face. And the reason for that is that one of the patterns that your retina is picking up is the facial configurations of human beings specifically, because that's really important to us. And that's delivered to a specific part of your brain. It seems to be, at least in part, the amygdala. And what the amygdala does basically is says, this, I don't know, that's not very good, this means this. So it maps that pattern onto this pattern. You don't need to see anything for that to happen, right? You just have to translate the pattern into motor action. Lots of animals see that way. So like when a fly flies by a frog, the frog doesn't see the fly and think, well, there's a fly, and then like nails it with its tongue. It's like the fly flying by pattern activates the tongue sticking out pattern. And it does it in like 1/100th of a second, obviously, because like, have you ever tried to catch a fly with your tongue? It's not easy, but a frog can really do it. And the fact that the frog's visual system is so simple and specialized means that there's hardly any neural connections between the perception of the pattern of the fly and the motor response. Like maybe there's 2 neurons intermediating. And so that frog can nail that fly right now. Whereas you're going to like wait around till you see the fly, and then you're going to swat it, and the fly sees this. And it's like it's gone in a week of fly time by the time you hit the table with your fly swatter.